My name is Dr. Leanne Swain. I'm a cell biologist and neuroscientist. Actually, what I will do first is I will start recording, although it looks like someone already started that for me. So I'm a cell biologist and neuroscientist and associate professor at the University of Victoria. I'll be your moderator tonight. Please bear with me as, although I've previously presented at a Café Scientifique, this is my first time acting as a moderator. So I'm fairly new to this platform. Clearly, there's still some technical issues that we're experiencing, even with the experts. So just thanks everyone for your patience in getting started tonight. Just for those who are new to Café Scientifique or who may be new to Café Scientifique, what this platform is set up for is to welcome scientific researchers affiliated with UVic to share their work with you, the community. And so pre-COVID, this was in person, and for the foreseeable future, it will be virtual on this platform, Blackboard. I've muted your microphones, and they'll remain that way for the duration of the talk. And then after the talk, I will unmute you, and we'll have about 10 minutes for questions until 7 p.m. for Dr. Yi. So without further ado, I'll introduce you to our speaker very briefly because he will also introduce himself. So we're super excited to have Dr. Kwang Moo Yi talking about artificial intelligence for machine vision tonight. So he was an assistant professor at the University of Victoria, and he is now at UBC, although he's still affiliated with UVic. And I will let him continue on with his introduction. Take it away.
Yeah, thank you so much for the introduction. I'm really happy to be here, although it's a virtual. Yeah, I think hopefully I can make this worthwhile. It would be so nice if these were in person, but that's a luxury that we can't afford these days, right? So I'll start by just relating myself a little bit more by introducing myself, but I thought since I've heard that Café Scientifique is a little bit more of a pub-like environment, I tried to also start introducing myself a little bit less formal in a way, just to give you a background story of how I came to work in these artificial intelligence topics. So about me. So I tried to look up my database of photos and tried to find the earliest possible me that I could find, and that's me. So that's me. I don't know how old I am. I don't even have a memory of this place. That's me always being 1 foot into my toys all the time and trying to also stay awake, apparently, probably, because I was always quite sleepy. Then well, I was a happy kid, and the thing that really led me to AI was something that happened when I was 10. I also tried to find a photo of me 10 years old, but I think I had just way too many photos that I couldn't really search through. So I found this instead. This was the thing that my dad at the time, working as a postdoc at Ohio, was working with. So this was this nice little robot named Kirby, and he showed this to a 10-year-old, and it actually walked. And that was the moment that really changed my life. And probably that is something that affected me quite a lot, having me wanting to work with robots, computers, and so on and so forth. So fast forward about 15 years later on, this is me very happy with my first ever major conference paper being presented at a place called ICCV, I think. It's a conference for computer vision stuff. And you can already see I'm pretty happy and probably overexcited that my enthusiasm carried on to the camera person that who took this, I guess. And you can see that there's a little bit of shake here. But well, that's how I got into AI, because computer vision back then, I had no idea it will end up being AI, but it ended up being AI at the end. So sort of a series of random events leading towards here to Switzerland, actually. So that paper was interesting enough, I guess, for some people in Switzerland to look at my profile later on when I apply for a postdoc and they offered me a job. So, hey, Switzerland. So I went there, and this is an actual photo that I took. So that's sort of my background history. So I started from South Korea at Seoul, lived my life until like late 20s there, finished my PhD, moved on to Switzerland to do my postdoc, and now moved again here to Canada in the West Coast to be a professor. And you can see that there's a little bit of pattern here, right? So I'll probably move like after 10 years to somewhere here for flat earthers. It might be out of the earth, but well, I don't know. I don't know where I will be, but hopefully I don't want to move actually. So now I'm studying machine learning and artificial intelligence, and with the interest of applying these to computer vision things. So today's topic, probably the word that drew you to trying to listen to me talking here today is probably artificial intelligence. But in fact, I will not talk about the artificial intelligence in the traditional sense. What I'm going to talk about is actually machine learning. So this might be a term a little bit less familiar to you if you are not in the field. So let me first try to explain what it is. And whenever we don't know some terminology, we always look up Wikipedia, right? So that's exactly what I did as well. So when I Googled machine learning, it led me to a Wikipedia page, and now this is what it means. So machine learning is a scientific study of algorithms and statistical models computer systems use. Well, that I read until here, and I know all these words, but it didn't really make sense at all to me. So I had to come up with something a little bit less wordy and a little bit simpler and also having most of these things inside. So turns out I think we can actually make that quite simpler to something like this. So AI nowadays is a little bit glorified, but what it is in a nutshell is basically given data. It's a big, black, gigantic machine that we don't know what's in there that basically spits out answers every time we put some data in. And the way we have these models is that we train them or alter them every time it makes answers, and then try to make it always spit out good answers. So that's all there is about machine learning, really. And it's everywhere, really. This is one of my dream cars these days, Tesla X. You know how Teslas drive themselves, right? So if you haven't seen it, I also brought this video in case you haven't seen it drive. And I also really like this video because it actually shows everything that I do in my research in a quick fancy demo. So you can see that on the right, you have these camera views and you see many things happening there. You see that the car seems to have understood what lanes are. You can see that's being drawn on the middle video here. And also things being recognized, and it's also doing something with the background, trying to see where things are moving and so forth. And it drives itself quite impressively. It might actually be a better driver than me, to be honest. And if you don't have a Tesla, well, you might have this nowadays, right? So you often have Amazon thing. I dare not say that word, especially given that a lot of you are at home right now, because it might trigger the word. And it does things for you. It recognizes your voice, it understands what you're asking it to do, and then it would order things, it would play music, it would do many things for you these days. And it's all powered by machine learning. And if that's still not convincing, you have probably cell phones. And within those cell phones, a lot of the things that these modern cell phones do are somewhat related to machine learning. For example, how your display searches show up, or even how, for example, if you Google a word, the order in which these things pop up could be understood as machine learning algorithms as well. So it's really everywhere. And you might think maybe it's a recent thing that this happened. But one very interesting thing is that this is not the first time AI and machine learning received this much interest. It actually received something like that in the past as well. So here's a video that I try to show and has a nice sound, narration and everything about what they thought the AI would be like in the past. This is a video made in the 60s or 70s, and there was an AI boom back then that really led people to believe that it will make a difference. In this video, you'll see that they even talk about men and women marrying AI. So that's also an interesting talk that they had, which they say that in the near future, you will have machines translating everything for you. Well, that was in the 60s. And you know that it never happened until 2000. And there is a reason behind that. And the reason behind that is that something called AI winter happened. And basically, the whole reason this happened is, well, what happened is that all AI research fundings were cut, people were disappointed, and there was no research to AI until very recently. Well, there were many reasons behind it, but let me show you what happened recently that revived all this AI so-called hype. So this is something that you could actually look at by searching at Google. You could actually see how many times people search the term deep learning. And this is their trend, and you'll see that something very much happened here that caused an exponential growth. That's around 2012. And what happened is many things, of course, but one very important thing that happened is related to this definition of machine learning that I showed earlier on, which is related to data. So in 2012, somebody created, well, this data set and had popularized this data set enough so that many researchers were actually working on it. It's actually 2009, but bear with me because the method that revolutionized everything came up at 2012. But what this is a gigantic data set, which is a collection of 14 million images of 22,000 categories. So what you see in the background, these very tiny images are actually images of the data set. And what these people did is that they collected data from the internet that are publicly available and labeled them what this image is about. And with that, they were now able to create sort of a challenge for researchers to work on, which is given an image, can you identify what's in this image, restricting what to 1,000 object classes. So for example, given this image on the bottom left here, you could output these classes, whatever algorithm you use, and then you would decide if it's good or bad by looking whether the answer is within this top 5. And well, when such a well-defined problem gets proposed, people work on it, and also it's a challenge. So if you're ranked 1, you get the fame. So people did work on it a lot. And one very interesting thing that this big, gigantic data set allowed was for this to happen. So in 2012, there was a method called AlphaGo that just suddenly appeared. And before that, these are some methods that we had before in our field. They were good, but you see a significant drop just happens here. And this is actually the first ever machine learning algorithm called deep networks that beat whatever method that was out there by a significant margin. And people started realizing that, hey, this method and its variants are working quite well. And what is behind them is actually data. And these methods were only possible to work like this because there were actually 1.4, 14 million images powering them behind. And the scary thing is that at 2015, they were actually better than average humans, at least for this task. So don't worry, they're not good for anything else than this task as of now. So data was what was actually driving this huge boom that happened. We had now access to millions of images, which people actually took time to label those millions of images so that we have the data answer pair, which we can then leverage to train the arrow that we had before. And in fact, this idea of data being super useful was not like unexpected. Like by 2009, these very smart people actually wrote an article. In the article, there's this saying that they argued. They went on and concluded that with all the things that are seemingly happening in the world right now with these machine learning or AI algorithms that are out there, it seems that data is probably the best ally that we have, and it's really unreasonably effective. And they go on to say that data is unreasonably effective, perhaps because some of these natural phenomena are as complicated as natural languages. We will never have these physical equations that we can use to describe them. And in that case, the only thing that we can have is data, and that's our best ally. And it's not only for like recognizing what is in an image, there are other things that data also boosted. For example, this is a task called object detection. Before I just describe these graphs in detail, I'll just show you what object detection is. So there's this algorithm called YOLO v3, and it's a method that gained a lot of popular interest because of the fast nature and what it could actually do. So what's happening right now is a machine learning method recognizing in real time where things are and what they are. You can see that they're not really perfect, but the rectangles that's shown here are not too bad. It recognizes what a car is, truck is, what a person is. These rectangles are similar to the ones that you've seen in Tesla vehicles as well. I don't know exactly what they're using. Of course, that's a company secret, but I'm pretty sure it's not too far off from what's happening here. You can see that it does quite well, and it runs this analysis in real time. What you're seeing here is recorded, but it does produce these outputs as shown like here. So this is a task that we like to do in our field, and then we measure it with performances with something called average precision, or AP for sure. And so higher the AP is, the better the performance is. And these are some data points that we collected for how the method works in terms of number of training samples it has seen in millions. So you can see that, well, if you use 10 million training samples, you get something called 20. And if you use 30 million samples, you get something like this. But the important thing here is there's a linear growth in terms of number of samples if you display it in log scale. So meaning that as the more data you provide, your algorithm just gets better and better and better without using anything. And to give you a little bit of perspective on how much growth this is from 20 to 30, that's about a decade's worth of research back in the days. Meaning that all you need to do is keep collecting data and you'll just get these for free. And that's one of the surprising things that we recently found out in our field on how important data is. So then again, the question becomes, why is it so useful? And why also suddenly we get to use this data like so? Because we must have had data for a very long time, right? And that is true. In fact, one of the main things that driving the effectiveness of data is also because now we have something called deep neural networks that can leverage data to its full potential. Long story short, the thing is nothing but such simple modules, but we have now a means to mathematically glue them together. So we could glue them together so that all of these modules that we have can be something called differentiated with respect to how good they're performing. And once we are able to do that, we could actually improve them as a whole to do better and better. And well, and because these are simple modules, we know their characteristics very well. And by meshing them together, we can build any complicated model. And that's basically why these data has been utilized so well nowadays. Because before, we couldn't do this. And we had to come up with a complicated model every time we would want to utilize some data. We don't have to. We just mash these building blocks together, and suddenly you now have some model that works quite well. But, well, as complicated it is, it's nothing but this blue arrow that I show here. In a nutshell, it's just something that transforms data into answers. And we just now have a lot of data and a lot of answers that we can use to enhance this blue arrow's performance. And speaking of enhancing these blue arrow performances, one thing very insightful in this quote here is actually this part. So these people have actually attributed the usefulness of data into a situation where we don't have the elegance of physical equations. And actually, in our group, research group, what we aim for is incorporating the physical equations, the physics equations that we have as our prior knowledge that we learned from school into machine learning. So it's not only us, actually. It's a recent trend of incorporating physics model into deep networks. So machine learning, data-driven plus prior knowledge is something that people like to do nowadays to also make machine learning AI more trustworthy, because we understand this part at least. And if the deep network part is data-driven and we don't understand clearly, still this part, the physics models could guide us in some way. So I was going to stop here briefly for questions, but I think since this is actually just a 45-minute presentation, you can also type questions in the chat. I will also answer them, but if you want to wait, I think we could also have the questions all aggregated to the end as well. So to now give you a little bit of idea of what we do. So I talked a bit about what machine learning is, what AI is, that it's nothing but just data to answers, and why suddenly it became such a big boom nowadays. So in our group, and now I will talk about what we do in our group. And in our group, what we do is actually threefold. So we do something called geometry, which is the question of actually trying to figure out how the world looks like just by looking at the image. So imagine this is your world and you only have this image with you. How would you actually try to relate the world with where you are and how it looks like? So that's the problem of solving for geometry, and which is what we do as our major application. And interestingly, the skills that we use to solve geometrical problems are also related to astronomy. So we also do some astronomy, which I will show just briefly what it's like. And of course, the reason I'm also associated with the Center for Biomedical Research, or was associated, is because I also do some biomedical imaging related applications. I will slightly touch on that as well. So first off, geometry. And what we do in our group, specifically, if you want to know the scientific terms to Google what this guy is actually doing, is called multiple view geometry. And it's a task of, again, figuring out how the world looks like and how or where you're situated in this world by just looking at an image. Well, we use multiple views, as the name suggests in this case, because if you were to just use one single image, unless you know what you're looking at, there's no way you can actually retrieve the 3D geometry, because light travels and then it will just hit a screen, and now you just lost how far the light traveled. The only information that you have in your image is what the color of the light that hit the image plane that you are observing. So, but with two cameras, you can actually do something different. With two cameras, you can actually figure out how the camera moved. And by figuring out how the camera moved, you can also infer the 3D geometry of the scene. And once you're able to do that, you could do some fun stuff like flying drones automatically and letting the drone behave according to the surroundings. For example, make it not crash into walls, or make it navigate automatically into a certain direction, a certain place, so that it delivers something, for example, like medical stuff. I was happy when I've heard that there was this example of medical delivery that happened with drones in South Korea when there was this big rain with floods and everything. That was one of the things that I would really love to do with AI. And so another thing that you could do, obviously, is what you saw before. Once you're able to do this multiple view geometry, you could also do things like self-driving cars. And Tesla vehicles probably do some 3D reasoning, otherwise they would not be able to drive safely, right? And another thing that I am recently interested in is actually firefighting. And the reason I'm interested in this is because this happens with firefighters. So driving, flying drones, those are things that humans can also do. But for example, in these circumstances, like you're inside a building with all the smoke filled in, if machines can actually help navigating in this environment, that would be great. So one of the things that I saw some companies do is they have now AR goggles, or AR, augmented reality goggles, that you could actually put on, where they would highlight how the structure looks like and imitate as if you're actually seeing through the smoke. So those are some potential applications that would actually allow humans to go beyond with the help of machine learning techniques. And of course, you can do things like this. So this is just a fun clip that I found, which is something back in the days, even before machine learning, which is that if you know how the world looks like, you can actually put some very interesting graphics things on shaders. Well, there are some image processing things to look like as if you're altering the world. So we call this a mixed reality experience. So those are all things we could do with multiple view geometry. And the physics knowledge that we use in our group is actually not too hard. So I'll just deliver the conceptual idea here. It's that, well, if you have some point that you could find in this image, and it turns out you could also find that point in another image, and they should correspond to, if they would correspond to a same physical point, what you could do is draw a triangle that goes through your first camera and the second camera and the physical point. And they should go through the points that you detected on the image plane as well. So if you have multiple of these triangles drawn, you could actually figure out statistically how this camera actually moved. And this is a mathematical knowledge that doesn't involve any machine learning, that doesn't involve any AI. It's just something that we know because we know that light travels in a straight line. At least we can approximate that it travels in a straight line in air, right? So that's the physics knowledge that we're using in our group. And it turns out that's very essential even in the day of machine learning. So that's the physical equation. And where the machine learning plays its role is not the physics equation, but to discover which points, because there are a lot of points here that we could use. For example, we could use this corner or some point in this window. Those are just things that we could select. So in the past, we relied on human intuition to select which are good and bad. Now, what we do in our group is to let data tell us which points are reliably detected across different images and which points are not. So that's what the machine learning tells us. So interestingly, the same technique is in a nutshell could be described as learning where to look in an image. And the things that we learn from learning to do that and learning to triangulate with those can be used to do something like this. So since what we use machine learning for is to discover where to look at, so we could actually do that not for that task, but something else, for example, learning to find where numbers are. So this is an example of us simply telling the machine that there is a number 1 and number 5 in this image, and number 3 and number 0 in this image, and so on and so forth. We would never tell the machine where it is. But since we know how to force the machine to look at certain regions, if we keep on showing those examples of image and existence of numbers, we can actually let the machine discover what's in an image and where it is automatically. So it was quite an interesting example that we were able to do, because that means, well, now we don't need to go and put bounding boxes in these numbers for us to train a number detector, for example. And also, since geometry is about shapes, we could also do things like this. We could also try to understand what the shape is. So here, this is a sort of a brain teaser for you to also wake up, because I've learned that after 30 minutes, people start sleeping whenever I talk. So this is a sort of a brain teaser that you could do to try to see if you can beat the machine. So here, within this dots, there is a continuous set of dots that will be linked together to form a number. It's quite hard, so I will reduce the number of noise dots that I put to make the problem a little bit easier. So that I reduced a bit. And if I reduce a little bit more, now some people might have recognized what number is in here. Yes, it's 4. So the same technique that we used, it's not exactly the same, but similar technique that we used for discovering where to look at or identify numbers in images could be used to identify numbers in a very contaminated situation like here. And in fact, machines, even with this amount of contamination in your data, could recognize up until 93% of the times, which is quite impressive. But don't get too scared, because this is just good for recognizing numbers. It can't recognize characters, digits, which we are much better at. So that's what we do for geometry in our group. And for astronomy, we do something like this. So I won't go too much into the details, but it turns out, well, at least from what the astronomers tells me, is that we could look at these weird signals we get by pointing a telescope at the sky at a certain stellar object, for example, Mars, Earth, or Venus, and tell what's in there. So, for example, this curve, this thing here tells you some element is existent in the star, well, planet actually, and this curve also shows you something else. So we can also do it for stars, and then understand how far they are, or how close they are, or what components that consist of those stars. For example, how much metal is in there, and these interesting things can all be discovered by these signals. But you see that these signals are very noisy, right? So it is hard to analyze them. And well, astronomers are great at it, but they're quite also packed with other things to do as well. So it would be great if there's an automatic algorithm that would be able to identify this. And that's one of the things that we're doing with collaboration of UVic astronomers and NRC astronomers to try to analyze this data here. And in case of biomedical imaging, this is something that I do with my collaborators back in Switzerland and also in South Korea. And what we did before is to do some analysis on MRI imaging. So what we do is not actually determining if there's cancer or there are malignant or benign samples in these images. What we do is somewhat a little bit more simpler than that. We just want to help doctors to do the actual diagnosis, because I can't really be sure of my algorithm would not make an error, but I do trust my doctors. So what we will do is not give them the answer, but give them better data. So here, this is a typical pipeline of how MRI works. In MRI, you have some random sampling going on your body. So what they do is they sort of cut through your body. Well, not literally, but they would just look through your body with some scan interval. And what they will do is they tell you to hold your breath, and they will aggregate those scans to form a rough full image, and they will try to fill in parts where the scan didn't go through, because each scan takes time and you can only hold your breath for so long, right? And where AI comes in here is to look at many examples of high quality scans and see whether we can turn a low quality scan into a high quality one. So that's one of the things that we do in our group as well. The relationship with geometry in this case would be that we also take into account how you should actually scan this. So looking at the high quality results that we have so far, we would try to figure out where to scan next so that we get even higher quality result. So those are some of the things that we do in our group. And I'm gonna end a little bit early, but I'm going to go back to the very beginning to give you the message that I want to deliver today. The message that I have here for you is really that all this machine learning and AI business that we're having here nowadays is based on data, and the data is what's driving all of that, and it's very effective. And perhaps what you want to do is make best use of your data by also incorporating physical knowledge of the world. So I have also everything in my presentation, most of them, as an open source project. So if you are one of those people who want to get your hands on these things and try them yourselves, there would be a slight learning curve, but you could also all try them with the code available on these sites. And I would be happy to answer any of your questions, I guess, starting from the question that I have on chat.
So
Awesome.
there was, oh, sorry. Go for it, Leanne.
That's okay. I just wanted to say, like, awesome presentation. Thank you. And yeah, let's start with the chat question.
So I guess I'll just read it. I guess Sean asked, can you explain what we should understand as what is AI versus what is machine learning? So I would say AI is a bit of a broader term. like for example, traditional AI had things like how would you create a logical decision process for you to act on a certain pattern, for example. Like you could think of this as, for example, in games, you have computer fighting against you in many games, right? The way those computer opponent acts could be understood as also AI, but it has nothing to do with machine learning. Well, at least up until back in the days. Like recently, it does utilize machine learning, but back in the days, it has nothing to do with data. It was actually some set of rules that you would create so that it achieves a certain goal. So, but with machine learning, it's more data driven. You have data and you want to compress it to a certain representation to make it useful for a certain task, or you want to directly make it output a certain answer that you will use. So that's you can understand this machine learning as a subfield of AI, which is quite data driven, and where you optimize and train to get your answers. So can you help? And the second question here I have is, can you help us understand how face recognition works as we use it on our smartphones? Yes, so there are multiple ways, but the first ever method that worked is something called AlphaGo. It's not a recognition software. It's first detecting software, and what it does is it just cuts image into multiple bits and then tries to has a set of cuts that is stored in memory that if everything goes through and you have this pixel value, you have a face at a certain location. So you're remembering these cuts. And that's how you used to detect faces. And now to recognize them, what you would do is you would have the face cut into a standard form, and you would keep on looking at multiple faces in the world to form sort of a compressed representation. And that compressed representation, if it's closest to you, your face, you say it's your face. If it's not close to your face, you say it's not your face. So that's sort of a high level explanation of how face recognition works. So the next question from Gills and Ilse Stevenson, I hope I didn't mispronounce your name, is how does my work relate to AlphaGo? It also uses data, but on that basis. Yeah, well, I'll just answer how it relates to AlphaGo. So I might just go. Oh, I actually left that slide out. So yeah, so AlphaGo is a technique where you are actually playing against yourself to create your answer to imitate. So remember, machine learning is all about data to answer. But now with AlphaGo, the thing that you do is you also create answers while you're trying to generate that arrow. So what you do is you play against yourself, and now you would have a winner and a loser, right? And if you put some randomness here, you would have randomly winning moves and randomly losing moves. Now what you will do is you will try to keep on adjusting the arrow that you had so that you start following the randomly winning moves. So that's a very rough explanation of how AlphaGo works. And there are some tweaks in there for example, to generate more randomly winning moves, but that's really the gist of it. So another question here is whether can face recognition adapt as we age and our appearance changes? That's a tricky question. And actually, I think we can make them adapt, but we can't do it right now, I would imagine. But we have some cool stuff recently that shows that if you take a certain human being face you could actually change it to 20 years earlier, 20 years later. You could even have a video of that person aging created. We have no guarantees that they will be accurate, but it does look reasonable. But I would not use it for verification purposes yet. Okay, so I guess that's the questions in chat. I would also love to speak to a human being.
I think we're going to keep the questions to the chat just for simplicity. So bring on the questions. These are great questions. And you're doing a fantastic job of fielding them.
Yeah, hopefully I don't misdirect people into too simplified answers here.
No, that's great.
Yeah.
You're making it really accessible. It's awesome. I'm sure that there's probably another burning question out there from somebody.
Yeah.
Sean, do you have another question? I see that you lowered your hand. But if you have another question, please add it to the chat.
You can also ask about me. I did put some effort in putting the baby photo of me. You can also ask what happened. Your baby you is so cute and you're not anymore. Yeah, that's a valid question that I also ask myself. So.
Oh, it looks like we have another question.
Yeah, military applications. Yeah, I'm strongly opposed to them. And while my techniques do have some implications, for example, flying drones automatically might lead to some things, but I would say those are some things that we as researchers have somewhat a dilemma. So some of these techniques, the same technique could be used to save lives, for example, like delivering medical supplies when humans can't. But then there's also the dark side, I would say, for killer robots, right? I really think it's like if you make a knife, you could also make a kitchen knife at the same time as making a weapon. So I personally would never work on a topic that is too much close to military, but at the same time, I would also hope that the humanity is sane enough not to create those things, because the technique is out there already, and the only thing preventing us from doing these things is our conscience, I think. Yeah, you can tell that I am mixed. I don't have a clear answer to that as well.
I was just going to say, Kwang Moo, this is John here. In case you actually wanted a question from a human.
Yay!
And I thought you answered Gayla's question very well, but I guess I've got a not unrelated question, which is, we saw the Tesla, for example, driving along, capturing video and using machine learning techniques to pass that information into sort of an assessment of what the world is doing.
Mm-hmm.
I can see in the future there's going to be a lot of privacy concerns over image capturing and how we use that information. And I think you make a good point that innovators can't do everything on their own. There has to be a partnership between innovation and legislation.
Yes.
And what do you see kind of the future path with some of the things you're doing in that light?
So that's a very good question, because we are aware as researchers that that's going to be a concern as well. So there are research that we're trying to do to actually make those privacy considerations to be embedded in the algorithms. For example, when you capture these scenes, well, you don't need to capture faces, for example, right? You don't need to capture human, what they're wearing, where they're going. You just need to know that a human being existed there. So you could actually try to put the put some pre-processing in there so that all of that information is masked out and you can't actually reconstruct it at all. And then you could enforce this to be something that you use for these cars or these other devices that you capture as a front end that you should never break, right? Then those enforcements could help deal with some privacy issues. And those are really legitimate concerns that we are dealing in our field as well. There is something, yeah, like privacy preserving methods for computer vision is actually an active research area.
A little while ago, I actually saw, oh, this is Ian, by the way.
Yeah.
I saw a startup that used machine learning to analyze potentially cancerous moles. Now that had to be validated by a physician, but is there anything different between those two applications, between mole identification and facial recognition, except for, say, the data set?
So I would say those are quite similarly looking from a high level point of view, but they're quite different in terms of detail. For example, what you're trying to do is classify if something is good or malignant or benign, whereas in the facial recognition, what you're trying to do is you're trying to figure out which person's mole this is, basically. So, and those two, while might be a small difference, is quite a big difference, because in one sense, if you have all types of malignant moles, then of course you could use the same technique to say this is a malignant mole. But now that's not possible, right? So what you can do is, for example, in terms of facial recognition, it would be similar to the problem of trying to identify all of my ancestors, for example. If you look at a photo and you saw me, you saw my mother, you saw my father, now you're supposed to figure out whether a person is my ancestor or not. So that's the difference that these two methods are having.
Fair enough. So it's more about how the question is phrased.
Exactly. And the difficulty here is really that now, in case of malignant and benign, you can't really cover all the different cases, whereas in facial recognition, you can more or less cover all the aspects of a human being by taking multiple photos, right? So that's also something that becomes very tricky. And I think I know the startup that you're talking about. And yeah, I don't know. I want to try their thing at the same time. I also would definitely go see a doctor first as well.
I have a question. I think I see a comment in the chat, which seems a bit difficult, maybe for you to answer. But I guess in the meantime, I just had a question for you, just relating to what your thoughts are on the importance or some of the issues about diversity and AI and machine learning, and like how important it is that what we put in will relate to what we get out. And yeah, do you have any comments on that issue?
Yeah. So this is sort of a half stroke that somebody made. Is that there was this company who worked on autonomous driving and pedestrian detection and like accident prevention. And that person said, like, if you were living in this part of this Europe, and now you're safe because the car will always recognize you and stop. But if you're from another part of the world, sorry, like that's sort of the difficulty that machine learning has. It has high reliance on the data and the variety in the data. You might have also seen the Google incident where they had only Caucasian people in the data set, and now some other ethnic people uploaded their photo and it was all gone wrong, right?
Yeah.
So there are those concerns, and these are very serious concerns. that people are now beginning to recognize. There's also effort in diversifying these data and making sure that when we use these machine learning methods for some critical applications, we always make sure that they are interpretable or as best as we can, and see whether there's any unfair biases in the data set that we use creeping into our explanations. So
Nice.
those are still very much active field of research, and we are aware of that.
That's so good. That's a great answer. Thank you.
Yeah, and yeah, that's a tricky question in the chat, saying
yes.
yeah, wonderful civilian everyday advances, but because government will fund military sooner than civilians. Yes, I hope now with all the openness of the internet and the widespread open research culture that we have with AI, this does not happen again. Right? Even without government funding, there are a lot of people doing research with. There's enough funds that we could be selective actually in researching AI. I think, and I think we have now control over which part of AI that we want to research the most. Especially in Canada, there's a very nice funding system that aims more on the spreading of research than like concentration of funds, which I really love, and one of the reasons I'm in Canada right now. And I hope that works out and it doesn't happen again like Oppenheimer.
Nice. Thank you, Kwang, so much for an amazing presentation and for fielding all these extremely difficult and controversial questions. You've done so awesome, and it's been a real pleasure to hear your expertise in this exciting and ever-changing area. So I just want to thank, on behalf of all the people I'm sure would be clapping if you could hear them, just want to thank you for such a wonderful presentation and for sharing your expertise. I just want to remind everyone. Yeah. And I just want to remind everyone that the next sort of CBR talk will be on the 13th with Karun Thenjiver. Actually, this might be just a general, maybe not CBR specific, but it'll be Karun Thenjiver from Physics and Astronomy. And he'll also be talking about machine learning with neural networks. So that should be fun. And I hope you're really enjoying the west coast of Canada, and it's a really nice place to live. Really glad we had you for a little bit at UVic, and hope you're enjoying being now at UBC, still on the west coast, which is great. And I see a bunch of thank yous coming in on the chat. I'm not sure if everything shuts down right at 7, so maybe John can tell us what's going to happen next. But just in case, I just wanted to get that in, and really thank you so much for such an awesome presentation.
No, you did a great job, Leanne. And we don't shut down immediately at 7. There's a little bit of a buffer, but just kind of as a acknowledging everybody's busy lives, we tend not to keep people beyond 7. But Kwang Moo, I was just going to echo Leanne's thanks, and thanks for a wonderful evening. It was great to hear you.
Yeah, it was fun for me as well. Yeah.
Oh, that's awesome. Thank you so much for all your amazing work as well. It's such an interesting and important area. So keep it up.
Thank you. I'll try.
And nice to meet you virtually.
Yeah, same here.
Okay. Have a good one. And thanks again. Thanks everyone for joining tonight. And thanks, John, for all the technical help, and Ian for the technical help and moderating as well.
That's great, Leanne. So I'm just going to turn off the recording now.
Sounds perfect.
I'll take care of that.